Hello students, today we are going to discuss reactions of aldehydes and ketones. In the previous class, we discussed the nomenclature of aldehydes and ketones, preparation and physical properties of aldehydes and ketones. In continuation of that video lesson, today we are going to discuss reactions of aldehydes and ketones. Contents of the today's topic: oxidation reactions of aldehydes and ketones, reduction reactions, nucleophilic addition reactions, aldol condensation and Cannizzaro reaction, iodoform reaction. Oxidation of aldehydes. Addition of oxygen or removal of hydrogen is called oxidation. Aldehydes are easily oxidized to carboxylic acid. In general, we can write an equation RCHO gives rise to RCOOH. Strong oxidizing agent such as potassium permanganate may be used. Acidified potassium permanganate or alkaline potassium, acidified potassium dichromate or alkaline potassium permanganate may be used as oxidizing agent. Acidified potassium dichromate means K2Cr2O7 and H2SO4, alkaline potassium permanganate KMnO4 and NaOH. So these are strong oxidizing agents. Mild oxidizing agent such as silver oxide Ag2O in aqueous ammonia may also be used. Tolerance test differentiate between aldehyde and ketone. We will discuss tolerance test in the next topic. RCHO, if undergoes oxidation, gives RCOOH. It means that in the presence of strong oxidizing agent such as K2Cr2O7 H2SO4 or KMnO4OH-, aldehyde is oxidized to carboxylic acid. Exercises. Examples are given. Pentanol. Pentanol upon oxidation with K2Cr2O7 and H2SO4 gives pentanoic acid. In this reaction, aldehyde group is oxidized to carboxylic acid, means bond CHO is converted to bond COOH. Tolerance test or silver mirror test. In the laboratory, tolerance test may be used to distinguish between an aldehyde and ketone. Tolerance reagent, a solution of Ag plus AgNO3 and ammonia, oxidizes aldehyde but not ketone. Tolerance reagent means ammonical silver nitrate solution. Ammonical silver nitrate solution is also called tolerance reagent. In this tolerance reagent, active species is Ag2O. So aldehyde oxidizes silver oxide to metallic silver. Silver oxide is reduced to metallic silver and aldehyde is oxidized to carboxylic acid. Since tolerance reagent is an oxidizing agent, it undergoes reduction. Ag2O is reduced to Ag. Therefore, silver mirror is deposited. The silver ions are reduced to metallic silver, which form a layer called a silver mirror on the inside of the container. If you look at the reaction, R bond CHO gives rise to R bond COO minus plus Ag precipitate. Ketones do not give silver mirror test. So tolerance test can be used to identify aldehyde from ketones. Only aldehydes give positive test for tolerance with tolerance reagent, whereas ketones do not react with tolerance reagent. Now, reduction of aldehydes. Reduction means addition of hydrogen or removal of oxygen. Addition of hydrogen or removal of oxygen is called reduction. Reduction of an aldehyde gives a primary alcohol. Reduction of an aldehyde gives a primary alcohol. R bond CHO upon reduction gives R bond CH2OH. In this reaction, aldehyde group is converted to alcoholic group, the two primary alcoholic group. Aldehydes can be reduced to alcohol by hydrogen oblique nickel or hydrogen oblique palladium or LiAlH4 or NaBH4. So, hydrogen in the presence of a catalyst nickel or hydrogen in the presence of a catalyst palladium may be used for this process of reduction. Otherwise, lithium aluminium hydride LiAlH4, short form LaH, may also be used as a reducing agent. NaBH4, sodium borohydride, may also be used as a reducing agent. Anyhow, reduction of an aldehyde gives a primary alcohol. Look at the reduction of acetaldehyde. CH3CHO is acetaldehyde. IUPAC name is ethanol. When ethanol undergoes reduction in the presence of lithium aluminium hydride, ultimately gives ethanol. It means that aldehyde group is converted to alcoholic group. In order to convert an aldehyde group into a primary alcohol, we can make use of the process of reduction. We can use hydrogen oblique nickel or hydrogen oblique palladium or lithium aluminium hydride or sodium borohydride as reducing agents. Next, nucleophilic addition reactions. Aldehydes and ketones undergo nucleophilic addition reactions. Addition reaction is a chemical in which two molecules combine to give a single product. So, two types of addition reactions are possible, but in case of aldehydes and ketones, they undergo only nucleophilic addition reactions. Why? Because in an aldehyde or ketone, CO group is present. That carbonyl group is a polar group. Due to the high electronegativity of oxygen atom gets partial negative charge, and due to the low electronegativity of carbon atom gets partial positive charge. So due to the high electronegativity of oxygen, carbonyl oxygen gets partial negative charge and carbonyl carbon gets partial positive charge. Therefore, CO group will be a polar group. Since CO group is a polar group, Nucleophile may attack on carbonyl carbon of CO group. The addition reaction begins by attacking of nucleophile over carbon of carbonyl group. When nucleophile attacks, intermediate product is formed. Afterwards, electrophile may attack so that we get the final product. So addition reaction means a chemical reaction in which two molecules combine to give a single product. Aldehydes and ketones undergo addition reactions. Number of addition reactions are possible in aldehydes and ketones. Similarity is there between the addition reactions of aldehydes and ketones because both contain CO group, and since CO group is a polar group, all those reactions which occur in aldehydes may also occur in ketones. So we can study the nucleophilic addition reactions comparatively or simultaneously. We can study the addition reactions which occur in both aldehydes and ketones. Let us discuss the addition reactions which occur in aldehydes and ketones. First one is HCN, addition of hydrogen cyanide. During the addition of hydrogen cyanide, cyanohydrin will be formed. So cyanohydrin will be the addition product when an aldehyde or ketone reacts with HCN. Similarly, aldehydes and ketones may also react with ammonia and its derivatives. When aldehydes or ketones react with ammonia or its derivatives, we get addition products. Hydrazine, hydroxylamine, phenylhydrazine, 2,4-dinitrophenylhydrazine. These are all the derivatives of ammonia. Grignard reagent. Aldehydes and ketones may also react with Grignard reagent. When they react with Grignard reagent, we get alcohol. When an aldehyde reacts with a Grignard reagent, we get a primary alcohol. When a ketone reacts with a Grignard reagent, we get a secondary alcohol. Nucleophilic addition reaction. The carbonyl groups in aldehydes and ketones are polarized because of the difference in the electronegativity of carbon and oxygen. The carbon atom carries a partial positive charge, while oxygen atom carries a partial negative charge. Aldehydes and ketones are susceptible to attack both by nucleophiles at the carbonyl carbon atom and by electrophiles at the oxygen atom. Look at the structure of carbonyl group. Carbon gets partial positive charge, oxygen gets partial negative charge. Therefore, nucleophile attacks on carbonyl carbon and electrophile attacks on carbonyl oxygen. Nucleophilic addition reaction of hydrogen cyanide, sodium bisulfite, Grignard reagent. Cyanohydrin may be formed using liquid hydrogen cyanide with a catalytic amount of sodium cyanide or potassium cyanide. Aldehyde or ketone, when reacts with HCN, gives cyanohydrin. In this reaction, initially Cn minus, that is cyanide ion, attacks on carbonyl carbon. Later, electrophile attacks on O minus so that cyanohydrin will be formed. Example, when acetaldehyde or ethanol reacts with hydrogen cyanide, gives acetaldehyde cyanohydrin. acetaldehyde cyanohydrin or ethanol cyanohydrin. Its IUPAC name is 1-hydroxy 1-methyl propane nitrile. When an aldehyde reacts with HCl gives cyanohydrin, this cyanohydrin is an unstable compound. The question arises, why cyanohydrin formed from an aldehyde or ketone becomes unstable? Because in cyanohydrin, Cn and OH both are negative groups are bonded to the same carbon. Whenever two negative groups are bonded with the same carbon, such compound will be very unstable compound. Therefore, here cyanohydrin undergoes hydrolysis in the presence of an acid, gives carboxylic acid. Example, when ethanol reacts with hydrogen cyanide forms cyanohydrin, that is 2-hydroxy propane triide, propane nitrile, 2-hydroxy propane nitrile. This 2-hydroxy propane nitrile undergoes hydrolysis in the presence of acid, giving rise to lactic acid. Its IUPAC name is 2-hydroxypropanoic acid. If you see the mechanism, Cl- is attacking on carbon of carbonyl group forming an intermediate. This intermediate gains a proton forming cyanohydrin. When shaken with an aqueous of sodium bisulfite, most aldehydes and ketones formed carbonyl bisulfite, a colorless crystal. The reaction takes place more readily with aldehydes than with ketones. The nucleophile is the hydrogen sulfite ion HSO3 minus. See, when an aldehyde or ketone combines with sodium bisulfite gives an addition product. In this nucleophilic addition reaction, nucleophile is hydrogen sulfite ion, that is HSO3 minus. Example, when ethanol, that is acetaldehyde, combines with NaHSO3, that is sodium bisulfite, giving rise to an addition product, that is ethanol sodium bisulfite or acetaldehyde sodium bisulfite. Condensation with hydrazenes, hydroxylamines and phenylhydrazine. See, hydrazine, that is N2H4 or NH2 bond NH2. Hydroxylamine NH2 bond OH. Phenylhydrazine C6H5NH bond NH2. So these are the derivatives of ammonia: hydrazine, hydroxylamine and phenylhydrazine. Aldehydes and ketones condense with ammonia derivatives such as hydroxylamine and substituted hydrazenes to give imine derivatives. Reaction with hydrazine. Hydrazene's derivatives react with aldehydes or ketones to form hydrazones. Hydrazine, phenylhydrazine, 2,4-dinitrophenylhydrazine. These are all the derivatives of hydrazenes. Whenever an aldehyde or ketone reacts with hydrazine, gives hydrazone. Example, benzaldehyde. When benzaldehyde reacts with hydrazine, gives benzaldehyde hydrazone. It means that aldehydes or ketones when combined with hydrazine form hydrazones. Condensation with example, reaction with hydroxylamine, NH2 bond OH. It's a derivative of ammonia. Hydroxylamine reacts with ketones and aldehydes to form oximes. Remember, aldehydes and ketones when combined with hydroxylamine form oximes. Oximes contain C double bond N bond OH group. Aldehyde or ketone combines with hydroxylamine giving rise to oxime. Example, when butanol reacts with hydroxylamine forms butanol oxime. Reaction with phenylhydrazine. When an aldehyde or ketone combines with phenylhydrazine gives phenylhydrazone. Example for this reaction, when butanol combines with phenylhydrazine forms butanol phenylhydrazone. Reaction with 2,4-DNP, that is dinitrophenylhydrazine. A solution of 2,4-DNP in methanol and H2SO4 is called Brady's reagent. This 2,4-dinitrophenylhydrazine is used to identify carbonyl group. Both aldehydes and ketones give 2,4-DNP test. Aldehydes react with 2,4-DNP at room temperature to give a yellow-orange precipitate of 2,4-dinitrophenylhydrazone. Look at the example. 2,4-dinitrophenylhydrazine when combines with benzaldehyde gives benzaldehyde 2,4-dinitrophenylhydrazone. Similarly, this reaction is also possible with ketone. R bond, CO bond, R is the ketone. When a ketone combines with 2,4-dinitrophenylhydrazine gives 2,4-dinitrophenylhydrazone. 2,4-dinitrophenylhydrazones have characteristic sharp melting points. The formation of a yellow or orange precipitate when 2,4-dinitrophenylhydrazine reacts with an organic compound at room temperature is used as chemical test for aldehydes or ketones. Already I told you this 2,4-DNP test is useful to identify whether the given compound is aldehyde or ketone. To identify an aldehyde or ketone by measuring the melting point of the 2,4-dinitrophenylhydrazone formed. By measuring the melting point of 2,4-dinitrophenylhydrazone, the given compound can be identified whether the given compound is an aldehyde or ketone. Anyhow, 2,4-DNP is used to identify the CO group present in aldehyde or ketone. Condensation, Aldol condensation. Before we discuss Aldol condensation, we must know the meaning of condensation. Combination of two or more molecules with the loss of a small molecule such as water or an alcohol is called condensation. Combination of two or more molecules with the loss of small molecule like alcohol or water is called condensation. Next, aldol condensation. Aldol condensation is one of the characteristic properties of aldehydes and ketones. Aldol condensation involves the nucleophilic addition of an enolate ion to another carbonyl group. See, aldol condensation is possible whenever an aldehyde contains alpha hydrogen. Those aldehydes and ketones which contain at least one alpha hydrogen involved in aldol condensation. So aldol condensation is possible both in aldehydes and ketones. The product, a beta hydroxy ketone or aldehyde, is called aldol. For example, if two molecules of an acetaldehyde undergo aldol condensation, we get beta hydroxybutyraldehyde. Commonly we call it as aldol. Why? Because beta hydroxybutyraldehyde contains aldehydic group and alcoholic group. So the product which contains both aldehyde and alcohol, such product is called aldol. This reaction is for aldehydes and ketones that have alpha hydrogen atom. So acetaldehyde or ethanol undergoes aldol condensation. Similarly, acetone or propanone also undergoes aldol condensation. Look at the reaction of aldol condensation. RCOCH3, R bond, CO bond, CH2R plus RCOCH2R. Then we get aldol. Cannizzaro reaction. Cannizzaro reaction. It is a chemical reaction that involves the base-induced disproportionation of an aldehyde lacking a hydrogen atom in the alpha position. So those aldehydes which do not contain alpha hydrogen, means hydrogen atom at alpha position, only undergo Cannizzaro reaction. For example, formaldehyde. Formaldehyde doesn't contain alpha hydrogen atom. Similarly, benzaldehyde C6H5CHO also doesn't contain alpha hydrogen. Therefore, benzaldehyde undergoes Cannizzaro reaction. So those aldehydes which do not contain alpha hydrogen or hydrogen atom at alpha position only undergo Cannizzaro reaction. Disproportionation or oxidation reduction reaction. Cannizzaro reaction is also called oxidation reduction reaction. Why? Because in this Cannizzaro reaction, one molecule of an aldehyde undergoes oxidation, another molecule of an aldehyde undergoes reduction. Therefore, we call it as oxidation reduction reaction, in which the same element is both oxidized and reduced. Cannizzaro first accomplished the transformation in 1853, when he obtained benzyl alcohol and benzoic acid from the treatment of benzaldehyde with potash, that is potassium carbonate. Look at the reaction. In this disproportionation reaction, one molecule of the aldehyde acts as an oxidizing agent or oxidant and converts a second molecule of an aldehyde into a carboxylic acid, while consequently being reduced to an alcohol itself. So in Cannizzaro reaction, we get two products. One is carboxylic acid and another is alcohol. Look at the example. Here benzaldehyde is taken into consideration. When two molecules of benzaldehyde undergo Cannizzaro reaction, ultimately we get benzyl alcohol and benzoic acid. Some more examples for Cannizzaro reactions are seen. Here in this example, 2 CH3-3-CCHO gives rise to CH3-3-CCOONA plus CH3-3-CCH2OH. So when this aldehyde, here the aldehyde doesn't contain alpha hydrogen atom. When the aldehyde doesn't contain alpha hydrogen atom, aldehyde with no alpha hydrogen, aldehyde with no alpha hydrogen doesn't undergo Cannizzaro reaction. Aldehyde with alpha hydrogen atom undergoes aldol condensation. Aldehyde with alpha hydrogen undergo aldol condensation to give aldol product. Aldehyde with no alpha hydrogen atom undergo Cannizzaro reaction, giving rise to salt of carboxylic acid and alcohol. One thing remember, we can compare this Cannizzaro reaction with the aldol condensation. Only the fundamental difference between Cannizzaro reaction and aldol condensation is that aldol condensation is only possible in those aldehydes which contain alpha hydrogen. Cannizzaro reaction is only possible in those aldehydes which do not contain alpha hydrogen. Reaction with the Grignard reagent. Reaction with the Grignard reagent. A Grignard reagent, a strong nucleophile resembling a carbanion R minus attacks the electrophilic carbonyl carbon to give an alkoxide intermediate. Reaction with the Grignard reagent. As you know that alkyl magnesium halide is known as Grignard reagent. In this alkyl magnesium halide or MgX, R minus MgX plus. So R minus is a nucleophile. Subsequent protonation gives an alcohol. So when a Grignard reagent resembling a carbanion attacks the electrophilic carbonyl carbon atom to give an alkoxide formation. When a Grignard reagent attacks on carbonyl carbon forms alkoxide ion. That alkoxide ion means RO minus on protonation gives ROH, that is alcohol. Example is given here, ethyl magnesium bromide. Ethyl magnesium bromide is a Grignard reagent. When it reacts with ethanol, gives an alkoxide. This alkoxide upon hydrolysis gives 2-butanol. So, Grignard reagent may react with the aldehydes, giving rise to alcohols. Here, ethyl magnesium bromide when reacts with acetaldehyde gives an intermediate product, that is alkoxide. This alkoxide upon hydrolysis gives a secondary alcohol, that is 2-butanol. These are about the reactions of aldehydes and ketones. In this lesson, we can conclude that aldehydes, both aldehydes and ketones contain CO group, that is carbonyl group. Since CO group is a polar group, it undergoes nucleophilic addition reaction. So those nucleophilic addition reactions which occur in aldehydes also occur in ketones. But addition reactions give single products. When we take oxidation reaction, aldehydes undergo oxidation reactions, ketones also undergo oxidation reactions, but the thing is that oxidation reactions occur vigorously or easily in aldehydes, whereas ketones undergo oxidation reaction with great difficulty. Anyhow, in rate of reaction, there will be change in rate of reaction. Aldehydes undergo oxidation reaction very easily, whereas the speed of oxidation reaction is slow in case of ketones. Most of the chemical properties of aldehydes and ketones are identical. When you take Aldol condensation reaction is possible in aldehydes. It is also possible in ketones. Reaction with ammonia is possible with aldehydes. It is also possible with ketones. Reactions with derivatives of ammonia means hydroxylamine, hydrazine, phenylhydrazine, 2,4-dinitrophenylhydrazine, all those reactions which are all those reactions in which aldehydes react with ammonia and ammonia derivatives are possible with ketones. So it shows that resemblance is there between aldehydes and ketones. Aldehydes and ketones not only possess identical chemical properties, but their methods of preparation is also same. Most of the methods of preparation of aldehydes and ketones are identical. Aldehydes can be obtained by the oxidation of alcohols. Ketones can also be obtained by the oxidation of alcohols. Only the difference is that aldehydes are obtained by the oxidation of primary alcohols, whereas ketones can be obtained by the oxidation of secondary alcohols. Anyhow, aldehydes and ketones can be prepared from alcohols only. Addition of hydrogen, that is reduction. Reduction reaction is also possible with aldehydes and ketones. Aldehydes and ketones undergo reduction reaction. For this reduction, we may use hydrogen gas in the presence of finely divided nickel, or hydrogen gas in the presence of palladium, or lithium aluminum hydride, or sodium borohydride. So these reducing agents may be used. One more property is also there, Clemmensen reduction and Wolff-Kishner reduction. So Clemmensen reduction, Wolff-Kishner reduction are not included in this video lesson, but they are also characteristic properties of aldehydes and ketones. Aldehydes undergo Clemmensen reduction. Ketones also undergo Clemmensen reduction. Only the difference is that reducing agents are different. In Clemmensen reduction, amalgamated zinc is used as a reducing agent. When aldehyde undergoes reduction, gives an alcohol in the presence of amalgamated zinc. Similarly, aldehydes and ketones undergo reduction in the presence of ethylene glycol and ethylene glycol and potassium hydroxide. This reduction is called Wolff-Kishner reduction. In Wolff-Kishner reduction, CO group is converted to CH2 group. CO group is converted to CH2 group. Means carbonyl group is reduced to hydrocarbon. carbonyl group is reduced to hydrocarbon. If ethanol or acetaldehyde acetaldehyde undergoes Wolff-Kishner reduction gives ethane. Why? Because CO is converted to CH2, so that ethanol is converted to ethane. So to convert an aldehyde into a hydrocarbon, corresponding hydrocarbon, we can use a reducing agent ethylene glycol potassium hydroxide and also hydroxylamine. Hydroxylamine, potassium hydroxide and ethylene glycol may be used as reducing agent. So this is the process by which an aldehyde is converted to a hydrocarbon. So these are the chemical properties of aldehydes and ketones. Thank you.